Hello once again, ladies and gentlemen, and thank you for joining me, Root Beer, as we take a look at the 2006 Cayley contest. And we're up to question number 11, the very first question in B part, where each correct response is worth 6 marks. So we're going to be trying to do our best as always. Triangle ABC has side lengths 6, 8, and 10, as shown. It's a right angle triangle. This is a Pythagorean triple. Each of the side lengths of ABC is increased by 50%, forming a new triangle, DEF. The area of triangle DEF is... Okay. So I can see two ways to do this question, which is a phrase I use a whole lot, but it's nice when there are multiple ways to do a question. So we have the option of either working out the new lengths. It'll still be a right angle triangle. We'll get base times height, and that'll be fine. But there's another way we can do this, which is by, we can see these triangles are going to be similar. And similar triangles have related areas in a very nice and predictable way. So I thought I'd talk about that. I will compute the side lengths as well for people who wanted to check that. But if I have one triangle whose side lengths are A, B, and C, and I get a similar triangle, and each of the side lengths is increased by some constant, some common ratio, usually we call it R, then the area of the first one, which maybe I'll call this area X, the area of our inflated triangle, our similar triangle, is R squared X. The lengths get multiplied by R, and the area gets multiplied by R squared. And this is not just an isolated phenomenon in 2 dimensions. If you had a 3-dimensional solid and you blew that up, you multiplied all its lengths by 2, the volume would get multiplied by 2 cubed, 2 to the 3, because you're in 3 dimensions. And if you wanted to imagine 4 dimensions, it would be multiplied by R to the 4, and things like that. Areas get multiplied by R squared, volumes get multiplied by R cubed, hypervolumes, R to the 4th. It's a nice little pattern, and it's something we can keep in our back pocket, exactly for questions like this. So, knowing this result, and that they give me the lengths for this triangle, 6, 8, and 10, I can quickly calculate the area. 1/2 base times height, 1/2 of 48 is going to be 24. And what does it mean to increase by 50%? Well, that's the same as multiplying by 1.5. In general, if we want to increase by n%, that's the same as multiplying by 1 plus n% over 100%. Okay, 50 over 100 is a half, so we get multiplying by 1.5. So our R is equal to 1.5. So our new area is 1.5 squared times 24, and that's 2.25 times 24. Or I guess I could write the 1.5, we could write it as 3/2. So then this would be 9 over 4, 24. I like that better because now the 4 and the 24 cancel out. 9 times 6, we're going to get 54 as our answer. And that is an answer of E down here. Okay, so that's certainly one way to do it. It's not the only way to do it. Of course, we could have increased each of these by 50%. And you could, again, use the multiply by 1.5 trick. Or you could say, well, what's 50% of 60? Well, it's half of 60. What's 50% of 8? I said 60, didn't I? I meant 6. Half of 6 is 3. Half of 8 is 4. Half of 10 is 5. So we add these on, and we get new lengths, 9, 12, and 15. And we can work with this triangle right here. And we can still do the 1/2 base times height. 1/2 of 12 is 6, and we get 9 times 6, so again, 54. So either way, what did I say that was? That was E, right? Yeah, E. And that's our answer for 11. So, in the next video, we're going to take a look at question number 12. I hope it's just as fun, and I will see you guys there.